Okay, welcome to my overview of temperature measurement systems. We're going to focus mostly on two, which are thermocouples and RTDs. This particular presentation covers a broad range of concepts. We're going to focus on some key concepts. We're going to skip over the really complicated stuff because many of the temperature systems that you guys deal with, they'll have been designed already. You're not going to design them. You're mostly out there to repair them, to help diagnose problems with them and that sort of thing. So we're going to focus on the core concept and skip over some of the more complicated systems. And so this particular presentation is from omega.com. So I urge you guys to go there. They have a lot of good source material on different measurement systems, and temperature is no exception. The focus of my video here is on thermocouples. We're also going to talk about RTDs, and you're going to learn a little bit about how they work. You can see little pictures of them. We're going to touch very briefly on thermistors. We're going to hit a little bit more strongly on infrared thermometry. Thermometry, there's a good word for you. Infrared is becoming more and more common because the chips to do it have become cheaper and cheaper and cheaper. And then we'll hit very briefly on other temperature controllers. And the last and probably most useful for you, if you've ever been asked to put a temperature measurement system in place, is how to choose. So you can probably help your boss out if you can provide him this data, if he's making the purchasing choice. And once you go up in your career and are buying some of these systems, you might want to hold on to this sort of presentation to help you choose the right temperature system for your application. So we're going to dive right into thermocouples. And in the thermocouples, you learn a key term. It's also in the book on page 47 called Seebeck effect. It's the fact that when you get two wires or two metals of any sort touching each other, if they're dissimilar metals, then current will flow. Just a tiny bit, but current will flow. And the greater in temperature change, then the greater in the voltage change for that flowing current. So that's a very important concept. So typically, when you take these two dissimilar wires I mentioned to you earlier, and you attach them to a voltmeter, because these wires are probably different than your voltmeter probes, then you're going to find that you're creating this junction, right? Down here, you can see this junctions 2 and junctions 3 are the connection points. And those junctions also create a tiny bit of current to flow and a little bit of voltage differential. And so you have a real problem in terms of measuring your actual temperature measurement if you've added into it extra voltage flowing because your voltmeter is different material than the thermocouple. So in essence, you have created J1 and J2. You know, you've got J1 as your kind of your hot junction. That's the junction where you want those two metals to touch each other, but that's what you're really looking to measure. And then you've got a different junction that's screwing you up. So it's keeping your measurement from being very accurate. And so how do we fix that? We create something called a reference junction. So on purpose, you create a junction that you can keep at a certain temperature, and then you have a known temperature setting. That cold junction, you can keep in an ice bath or just at room temperature. If room temperature is pretty consistent, then you know that your voltage you're generating out of J1 is the difference between the known voltage of your known temperature, say the cold junction in the ice bath, versus the junction that you're trying to get the measurement from. And that's usually called a hot junction, which is J1 out in the real world, or what you're trying to measure, and your cold junction measuring at a known reference point. You can use an ice bath, or you can use room temperature, depending on what you're trying to do. And so this is a typical setup for thermocouples. You're going to run into this in a variety of formats. That's assuming your thermocouple is the type with one copper lead. But since, like a J-type thermocouple, like the ones we're using here, one of the leads is iron. And so an iron to copper junction will create a small third and fourth junction point here. So that would add some more inaccuracies in your voltage measurement. So how do you solve that? We can create something called an isothermal block, and that's also mentioned in the book. The isothermal block kind of creates a point to make these connections that will allow for the temperature measurement transfer, so that you make sure that your junction 3 and 4 are exactly the same temperature, so their net effect is 0. Because if you have them in a position where one could be warmer than the other, then your net effect could be screwing up the accuracy of your target temperature measurement, T1. So does this make sense to you guys, or are you picking up what I'm pointing down here? These are different techniques to use to create junctions between your measurement device and your thermocouple to reduce errors. More commonly now, we have something called software compensation. And in the temperature controllers, the red line temperature controllers that you guys are going to be using in the lab, it has that built-in software compensation. It knows what material that it's got on its terminals, and it knows, depending on, you can select the right thermocouple to it that it's going to attach to those terminals, so it knows exactly how to allow for automatic adjustments based on temperature. So it knows that it's got that built-in adjustment in its own internal little computer, and that own internal adjustment that it's making automatically offsets whatever it shows you as your process variable, as your reading of the temperature. So that's really common out there. We also mentioned on this slide a very important term. Why use a thermocouple? They're not super accurate. Why use a thermocouple? Because they're cheap, small, flexible, rugged, and operate over a huge temperature range. We also have, for very accurate thermocouple systems, you can do some sort of hardware, ice point reference data. We're not going to get into that. I mentioned you could do a solder or welded bead on the end of your twisted thermocouple wires, or even just have them together. For instance, this little thermocouple that I have right here is just 2 pieces of metal welded together in a bead. And that gives me my thermocouple. So here's a few notes on when you're making your thermocouple beads, how to do it. And we also know that the thicker your wire, the slower it is to respond to temperature changes. So this gives you an idea of what that time over change is, depending on the wire type. We're not going to dive into details on this. It's a little bit more than we need to get into. However, on this chart right here, I pasted in a chart explaining the range of different thermocouple types and standard color coding. So you see the standard color coding for E, J, K, and T type, which are one of the most common thermocouple types that are out there. You'll see their temperature range and other fun data about that, including what materials they're made of.
What is Constantine?
Constantine is a kind of metal.
Which is a mixture of?
I don't remember off the top of my head. It is a mixture. It might even be an element. Hold on, that's a good question. What is Constantine? I don't remember.
Copper and nickel.
Yeah, copper and nickel. There it is.
Hmm.
Yeah, copper nickel alloy used for electrical work for its high resistance. Yeah. Copper nickel, how about that? Yeah, I mean, that's what the magic of the internet is. If you don't know what something is, you can look it up. So our J-type thermocouples you're playing with, we know they're J-type because there are white and red wires on them. Were copper nickel alloy and then iron. So here's a quick summary of different thermocouples. In my experience, J-type and K-type are hugely more common than any of the other type. J, K, and T are probably the most common out there. J is probably the single most common because it is cheap. One of the key limiting factors with buying different styles of thermocouples is the sheathing, the way you protect it. Obviously, the one that I showed you here is sheathed in ceramic beads. So this is designed for extremely high temperatures, 5,000 or 4,000 degrees Fahrenheit, very, very high temperatures, or anyway, right at the high end of the thermocouple, maybe not quite that hot. And so even if your thermocouple wire can handle the high heat, it probably won't be rated that high when you purchase it, depending on the sheathing. So the sheathing is very, very important. If you short out your thermocouples even the slightest bit, even have it resting near some other sort of grounding source, you will not get an accurate measurement at all. And plus, it's very sensitive to EMF. So if you have it running near a 120 volt, 240 volt line, sometimes that can be enough to screw up your measurements. And here's a list of sheathing and the different ranges that they can handle. And you'll see that ceramic beads can handle up to 1950 degrees C, which is pretty darn hot. So there's a lot of problems you can run into thermocouples. This is where, as a maintenance tech, you should start listening. If you see that the bead is cracked in the thermocouple, if you see it start to get pitted, it looks like it has a lot of surface damage. Chances are it's not really transmitting properly anymore, and you need to do something about it. Sometimes thermocouples, over time, the physical wire properties change. So they lose their calibration capability. So there's a couple things I should mention there. At very hot temperatures, the resistance of insulation changes. So the thermocouple might actually start getting some shunt impedance. That is, the resistance passes right through the insulation and you get kind of a virtual junction. And electrolytic dyes in water sometimes cause a problem. We also have thermal shunting. And they suggest small wires if you're picking up some thermal shunting. And noise, that's the noise that I mentioned. If you have a high voltage line running near a thermocouple wire, it could create noise. Basically, you could get a variety of problems. I'm not even going to go through all of them. Okay, I'm going to skip over some slides here. I will just pause on this side. This is a useful slide if you are installing a thermocouple in an application. And these are just pretty basic notes here. A lot of them are just obvious. Make sure all the materials are clean when you're installing them, especially when you're making your junctions, your connections with wires. If you have some corrosion on the wire, strip back to get to the clean area. It's very important. If you don't, then you will not get an accurate measurement with those devices. And here's a whole bunch of different good notes. Make sure you have the proper wire with the proper insulation for your environment. Make sure that if you pass a hair dryer or any heat source over the wire, it only changes temperature when you pass it over the bead, the very end of that thermocouple. If you're seeing a temperature change in the middle of the wire somewhere, that means you've got a break point and you've got a problem with your insulation. So that's enough on thermocouples. You guys good on thermocouples? So the key things are, make sure you follow the manufacturer's directions perfectly for selecting the right thermocouple and the right sheathing for the right environment. Make sure it's clean. Make sure you follow your manufacturer's recommendation for hooking up that thermocouple properly. Don't just strip it off and jam it in somewhere. Use their recommended connectors, their recommended method of wiring up. For instance, the book on the bottom of page 47 dives into, it has a picture of a thermocouple with a standard yellow plastic connector. And if you use that connector with that thermocouple, then you'll get a very accurate reading. And you don't want to goof around with your own connections. You can't just clip off a thermocouple wire and throw a wire nut on it to another wire. You will run into a problem.